or more compounds with the same chemical formula but different structural arrangements are called isomers. The phenomenon is known as isomerism. Isomers differ in one or more physical or chemical properties because of the difference in the arrangement of the atoms. Isomerism in coordination compounds may be broadly divided into two types: structural isomerism and stereoisomerism. Structural isomerism arises due to the presence of different kinds of bonds between the metal and the ligands. This can be further subdivided into several types, like ionization isomerism, solvate isomerism, ligand isomerism, linkage isomerism, polymerization isomerism, coordination isomerism, and coordination position isomerism. Of these, we will discuss only ionization isomerism, solvate isomerism, linkage isomerism, and coordination isomerism in this module. Let us first discuss ionization isomerism. Compounds that have the same stoichiometric composition but yield different ions in a solution are called ionization isomers. This type of isomerism is due to the exchange of groups between the complex ion and the ions outside it. The composition can be determined by a precipitation reaction. Pentaamine sulfato-cobalt 3 bromide and pentaamine bromido-cobalt 3 sulfate are two ionization isomers. The first isomer gives a white precipitate of barium sulfate with barium chloride solution, thus confirming the presence of free sulfate ions. By contrast, the other isomer does not give a positive sulfate test. It does give a pale yellow precipitate of silver bromide with silver nitrate, confirming the presence of free bromide ions. Other examples of ionization isomers are tetraamine dichloridoplatinum 4 bromide and tetraamine dibromidoplatinum 4 chloride. Let us now look at solvate isomerism, which is similar to ionization isomerism. This form of isomerism is known as hydrate isomerism if water is involved as a solvent. Compounds that have the same composition but differ by whether or not solvent molecules are present as ligands in the coordination sphere or are merely present as free solvent molecules outside the coordination sphere are known as solvate isomers. 3 isomers of chromium chloride hexahydrate CrCl3 6H2O are known. From conductivity measurements and quantitative precipitation of the ionized chlorine, they have been identified as the violet-colored hexa-aquochromium 3 chloride, the green-colored penta-aquochloridochromium 3 chloride hydrate, and the dark green-colored tetra-aquo-dichloridochromium 3 chloride dihydrate. These isomers have different chemical properties. On reacting with silver nitrate to test for Cl ions, we would find 3, 2 and 1 chloride ions in the solution respectively. The other type of structural isomerism is linkage isomerism. Linkage isomerism arises when a ligand can bind to a metal ion through any one of two or more different donor atoms. Thus, this type of isomerism is seen in the coordination compounds that have ambidentate ligands. For example, in the ambidentate nitrite ion, either nitrogen or oxygen atoms could act as the electron pair donors. Thus, there is a possibility of isomerism. Two different complexes, each containing nitrite ions, have been prepared. For example, red pentaamine nitrito-cobalt 3 chloride, in which the nitrite ligand is bound through oxygen, and yellow pentaamine nitro-cobalt 3 chloride, in which the nitrite ligand is bound through nitrogen to the metal ion. Similarly, the thiocyanate ligand, SCN, may bind to the metal through sulfur to give complexes of the type MsCN, or through nitrogen to give MnCS type of complexes. Coordination isomerism is another type of structural isomerism. This type of isomerism arises when both the positive and negative ions are complex ions. It may be caused by an interchange of ligands between the anion and the cation. For example, in the complex hexaamine cobalt 3 and hexacyanochromate 3, the ammonia ligands are bound to the cobalt 3 plus ion, while the cyanide ligands are bound to the chromium 3 plus ions. In its coordination isomer, hexaamine chromium 3 hexacyanocobaltate 3, the ammonia ligands are bound to the chromium 3, while the cyanide ligands are bound to the cobalt 3 plus ions. Let's now look at stereoisomerism. Compounds with the same chemical formula and chemical bonds, but different arrangement of atoms or groups in space, are called stereoisomers. Stereoisomerism can be subdivided into geometrical isomerism and optical isomerism. Geometrical isomerism is also known as cis-trans isomerism. It is seen in the heteroleptic complexes with coordination numbers 4 and 6. The isomer in which the two identical groups are adjacent to each other is known as a cis isomer, while the isomer in which the two identical groups are diagonally opposite to each other is known as a trans isomer. It is important to note that only square planar complexes show the phenomenon of geometrical isomerism, and not tetrahedral complexes. This is because the relative positions of the unidentate ligands attached to the central metal atom in the tetrahedral geometry are the same with respect to each other. In square planar complexes, compounds with the general formula Ma4 and Ma3b do not show geometrical isomerism. Here, M is a metal ion, while A and B are monodentate ligands. The square planar complexes shown here usually show cis-trans isomerism. The first complex is of the type Ma2b2. The best example of this type is diamine dichloridoplatinum 2. Both cis and trans isomers of this complex are shown here. The second complex is of the type Ma2bc. Diamine bromidochloridoplatinum 2 is an example of this type of complex. Another type of square planar complex is the MaBcD type. Platinum 2 forms a number of complexes of this type. Such complexes exist in three isomeric forms. For example, amine bromidochloridomyridine platinum 2. The three isomers of this complex can be seen here. Now, let's look at the geometrical isomerism in octahedral complexes. Ma6 or Ma5b types of octahedral complexes do not show geometrical isomerism. Complexes of the type Ma4b2 and Ma3b3 and complexes that have unidentate and symmetrical bidentate chelating ligands of the type MAA2b2 exhibit geometrical isomerism. Dichloridotetraamine cobalt 3 is an important example of a complex of the Ma4b2 type. The cis and trans isomers of this complex are shown here. An important Ma3b3 type of complex is trichlorido-tripyridine rhodium 3. In one of the isomers shown, you can see the three donor atoms of the same type of ligands occupying adjacent positions at the corners of an octahedral face. Such an isomer is known as a facial isomer. In the other isomer, called a meridional isomer, the position of the ligands are around the meridian of the octahedron. Now, let's look at MAA2b2 type of complexes containing monodentate and symmetrical bidentate chelating ligands. Here, AA is a symmetrical bidentate chelating ligand in which A and A indicate two similar coordinating atoms, while B is a monodentate ligand. The cis and trans isomers of dichlorido-bis-ethylene diamine cobalt 3 are shown here. Let's examine optical isomerism, which is the other type of stereoisomerism. When the solutions of certain coordination compounds are placed in the path of plane polarized light, they rotate its plane through a certain angle that may be either to the left or to the right. This property of a complex of rotating the plane of a polarized light is called its optical activity. A complex that possesses this property is said to be optically active. Complexes that rotate the plane of polarized light towards right are said to be dextro-rotatory or D-form, while complexes that rotated towards the left are called levorotatory or L-form. The D and L forms are mirror images and cannot be superimposed on each other. Such molecules or ions that cannot be superimposed are called chiral. Since these forms are related to each other as mirror images, they are commonly called enantiomers. Although optical isomerism is possible in a variety of octahedral complexes with unidentate ligands of the types Ma2b 2c2, Ma2b 2cd, Ma2b cde, and MABCDEF. We will restrict our discussion to complexes containing only bidentate ligands of the type MAA3 and complexes containing monodentate and symmetrical bidentate chelating ligands of the type MAA2B2. Trisethylene diamine cobalt 3 is the best example of an optically active coordination compound of the type MAA3, which has only bidentate ligands. The dextro and levo isomers of this complex are shown here. Dichlorido bis ethylene diamine platinum 4 is an example of an optically active coordination compound of the type MAA2B2 containing both monodentate and symmetrical bidentate ligands. Note that only the cis isomer of this complex shows optical activity. Its trans isomer shown here is optically inactive because its mirror image can be superimposed on itself.